Today I'm here to present you the results of meta-learning as a Markov decision process. And I would like to thank my collaborators Nadon Christian, Isabelle Guillon, Michel Sebag, and Amy Jan. Now, everyone knows that today the machine learning is enjoying a huge success from different application fields in language, computer vision, speech, and games. But unfortunately, behind those success, there is a huge human effort when we design the model architectures or tuning its hyperparameters. That means we are still not able to replace this human expertise by a machine. So when we talk about replacing the human expertise by a machine, we enter to the field of AutoML, or automatic machine learning. So first, what is an AutoML problem? So an AutoML problem can be formulated as if we have some pairs from the training examples x and y. We want to find a function f, which is function with some trainable parameters alpha, and how good is f is and what the alpha test value actually depends on what model we use, and the model is actually totally defined by its hyperparameters theta. So our goal here is to find the find a theta that minimizes some criterion j, or if you want, a loss function within some time limit. And this j, the loss function and the time, can depend on different tasks. So my first experience in AutoML is to have participated to the AutoML challenge in 2015. So the AutoML challenge in 2015 was organized by Isabelle Guillon, and in this challenge we provided 30 different data sets. So I mean 30 different data sets from different application fields. So you have image, medical, speech, and financial. And the goal of the challenge is to develop an AutoML system that delivers good algorithms on an unseen new data set. So after 1 month of hard work, I finished by placed the third in the final run. So I started my PhD, and I spent the first year to analyze the result we get from this AutoML challenge. And we have determined that the next bottleneck of AutoML will be meta-learning. So what is a meta-learning problem? A meta-learning is actually a method that helps you to learn a new task faster. So I mean, you find the best algorithm of a new unseen task faster given the previous experiences. So in other words, giving a bunch of machine learning tasks, so a benchmark suit, and we applied a lot of algorithms on them, so we can get the performance of the algorithms. And then if we put everything into matches, here we call metadata set, and we know this matches as. So in these matches, each row is a data set, and each column is an algorithm. And the value of the matches SDIAJ is actually the performance of algorithm J applied on dataset I. So I range from 1 to n-1, and J range from 1 to n, with n the total number of the datasets, and m the total number of the algorithms. And then the goal here is that I want to find a best algorithm, so the best as on a new task, so the last one, the DN. So I want to remind you here that we want to focus only on meta-learning. So here we want to get rid of the problem of overfitting or underfitting during the learning. So we suppose that every SDIAJ here we get is the true performance. That means we train the model very, very well, and then this performance we get actually reflects the generalization error. So every time when you curate one SDIAJ, you get the true performance. So we get rid of this problem. And the two difficulties in meta-learning problem is that, first, because one data set just provides one row in this matrix. So we are actually in a small data problem. And also, it's usually very hard to make all algorithms work on all data sets. So actually, we have missing values in this matrix S. So now I just give a picture of this whole idea. So the S here and the blue part actually means the data set you have seen before. So it's your previous experience. And the red line here is every time when you get a new data set, you kind of append it to the whole matrix S. And then at the beginning, you know nothing about this new data set, so it's just a totally empty line appended to the matrix. And here still, if you take the matrix as a standard machine learning matrix, we can say that each training example is a data set, and each feature is an algorithm. But be careful here, actually, the algorithms can be simply a learning machine or some meta features. So if you don't know, meta feature is some way to compute the statistical structure of the data set. Okay, so then actually it's because I just say we were in a very small data problem. So it's actually difficult to have large metadata sets. But thanks to the effort of many researchers, we still have access to some good of them. So here I just give two examples. The first metadata set comes from the AutoML challenge I just introduced before. So you have 30 data sets, and I benchmarked 17 algorithms on them. So totally it gives you a matrix of 30 rows or 30 lines times 17 columns. And the second comes from the OpenML platform. So OpenML is a platform that gathers different data sets and customized learning machines. So here we get a little bit larger matrix with around 80 data sets and 300 algorithms. And below, I just show the heat map of these data sets. So you can see a little bit the structure of them. Now, before I start introducing our matrix, our method, I would like to give a quick overview of all the methodologies of meta-learning we have now. So the first level is warm start. That means every time when you get a new data set, you actually start your searching from a point. So a point is an algorithm that has worked well in a similar previous task. And then you do your search. So this usually gives you a better search initialization. So one example using this technique is auto-sklearn. The second one is pre-training. So one famous example is that you can train a CNN with all the image from the ImageNet, and then every time when you get a new task, it just retrain the last layer to adapt it. And the third one is active meta-learning, or collaborative filtering, if you are more familiar with that, is that we take the whole matrix as a whole, and we treat the unknown performances in the red line as some missing values. And then we use matrix factorization to estimate those unknown performances. And then you just can select your algorithms according to these estimated performances. And next is we can also do some neural architecture search on the meta level. That means you learn a searching policy across different tasks, and then you transfer this policy to a new task. And finally, is review is the new stuff I'm going to introduce in this talk, is that we take the whole thing as a Markov decision process, and then we would like to use reinforcement learning to solve the problem. So in this talk, I will focus on two of our works. The first is Actimator. So actually is what I just introduced before, a collaborative filtering method. So this is actually a greedy method. Why? Because every time when you get the estimated performance, you actually get a ranking of algorithms. And then you choose your next move or your next algorithm according to this ranking. Then the second focus will be review. So here we formulate everything as MDP. So actually we are doing planning. That means I don't choose my next move because it's the highest. What my focus will be the long run, the accumulated performance over the long run. So it's, the two methods represent greedy and planning. Now let's get started with the greedy method, so or collaborative filtering. So what we have done here still, we have this famous matrix, and then so in blue part is your previous experiences filled with the performances you have tried before, and then it comes a new task. So at the beginning, we know nothing about this new task, so it's an empty line. This is called a cold start problem in collaborative filtering. So to solve this cold start problem, we need to first choose one first algorithm. Then you can have the right size of your matrix factorization. Actually, there are many ways to do this first choice, but here we just propose to use the algorithms with the highest median over all the old tasks you have experienced before. Once you have made this choice, we take the whole matrix and we do a matrix factorization. Here we use a specific algorithm called coffee rank, but actually you can use other things other than coffee rank. So what coffee rank does is to estimate the values in this row. And then the next one you want to choose is the argmax, so is the one with the highest estimated algorithm. So it's 0.9 here. Then you choose this one, you chain this, okay, sorry, I just forget. So every time when you choose algorithm here, actually you evaluate. That means you chain it and test it in this new data set. And then you kind of curate the true performance. So this is in blue, and in green is just an estimation. So every time you try a new task, a new algorithm, you get more information about your new task, and then you refresh your matrix factorization. And so we iterate all the steps now. So every time when you make a decision, you need to do a matrix factorization. Okay, so from this slide, I will show you the results of this active method on two different metadata sets I have showed before. So the first one is AutoML, so it contains 30 data sets. And then because 30 data sets is really small, so we are in a small data problem. What we propose to do is to do a leave one out evaluation procedure. So what I mean is that we meta chain on all 29 algorithms, all 29 data sets, and then we test on the last one. So it's like you take the 29 data sets as a blue part, and the last one like a red line before. And then how can we evaluate the algorithms, the meta-learning algorithms? So here we want to compare our method with 3 different baselines. So the performance of those algorithms will express as the best performance we have curated so far, up to each time step. So a good algorithm will have a curve that climbs very fast at the beginning. That means that you already find a good algorithms from the beginning, from very beginning here. So here we proposed a different baseline. So there are two types of baseline here. The first is random. So random is stochastic baseline. What I mean by random is that every time when you need to make a decision, you make it at random. And then we repeat 1,000 times. And in blue, we plot the median over these 1,000 times. And here, I just show the result for one particular data set. So in blue, you have the median of 1,000 random repeats. And this is actually a very difficult baseline because the random agent, so the random method has a very good performance on average, but it has a huge variance. So in shaded area, I just show the quantiles of these 1,000 repeat times. And then in red is our method active method. So you need to do one matrix factorization every time when you make a decision. And then in purple is kind of a speed up active method, is that now I don't do matrix factorization for each selection. I do it once just right after I see the first median. So once I solve the problem of cold start, I get my first algorithms, then I do once matrix factorization, you get the ranking, and then you choose your algorithms. You select your algorithm according to this only ranking. And then the green one is the simple rank with median. So here there is no matrix factorization at all. You just rank your algorithms according to the median over the past task, and then you select the algorithm according to this median. So these three things, these three baselines, so active method median with one coffee rank, and and the simple rank with median, they are deterministic. Why? Because every time when you make a decision, you make it according to a ranking. So here, what we can see is for this one particular text data set, we can see that over these error bars or these quantiles, our three methods at least work as well as the baseline. And then maybe you can say, okay, you just show me the particular very good one. So now I'm showing you the average over all the data sets. So if we do leave one out, actually we will test on all 30 data sets. So here shows the average, and we can still see that our method, these three things work at least as well as the random baseline, which is very difficult to beat actually if you see the average. Now the same thing, but this time with a larger metadata set, the AutoML. So here you have 17.6. And we can still see that active method at the beginning it loses a little bit, but then it climbs up very faster. And finally, as a whole, we can still say that it was at least as bad as well as the random baseline. But surprisingly, the simple rank with median was pretty well here. So that means we still have some research to be done in this field. Okay, so what we have seen so far is greedy. Now let's move from greedy to planning. So maybe you have already feel that everything that we have done so far is actually a sequential decision-making process, or more particularly a Markov Decision Process, or MDP in short. So in the MDP is defined by a four tuple: state, action, reward, and transition probability. So in our case, we can see that the state can be the partially filled row of the matrix. So the red row, the last red row of the matrix. And then the action is to choose the next algorithm to evaluate. Once you have ST and AT, you transit to ST plus 1, which is still the red line, but with one more value thanks to this AT. Then the reward you gain at this time t is actually the improvement over performance, over the best performance so far, minus some alpha is a factor. So it's actually a linear combination between the improvement over performance and the computational cost of the AT. What we do this, the reason is that we want the agent to adapt to the change of the alpha. And we want the agent to find the good algorithm as quickly as possible. But here, if we compare this setting with a standard MDP, actually we have some differences. The first difference, or first property of this thing is that we are in a finite time horizon. That means I limit the number of selections. I told the agent to only select like, okay, 10 times. Even I have 17 algorithms in all. I just allow it to act 10 steps. So this is a finite time horizon. The second is that our action A here only reveals more information about the state. It has no effect on data generating process. So this is different from a standard MDP. So we call this, the MDP with these properties as a review MDP. And we want to solve this review MDP with reinforcement learning. So actually, if you want, review is not only the meta-learning problem, it's a whole family of games. So you can, if you know, you have Battleship. And here, I just want to show you one example we have worked for the debug purpose. It's called MNIST game. So the MNIST game actually was introduced in the paper of Amy Zhang. And the original setting is that the agent faced to a fully masked digits, so in purple here. So at the beginning, the agent sees nothing. The image is fully masked. Then the agent needs to move progressively and review the pixel values. And the goal of the agent here is that I want to review to classify this digit, to say if a 0, or is a 2, or is a 1, etc. So the goal here is to navigate to classify the digits. And here, So in the original setting, the goal is to classify the digit. But then we modified the setting to make it more alike to meta-learning. So now everything's the same, but the goal here is to navigate to find the brightest pixel on the digits. It's like meta-learning because finding the brightest pixel is like you want to find the best algorithm or the highest performance in your role. So here you see the state. So the mask part is in purple, and then the reviewed position are in black and white. And here in green, we show the value function. So actually, this is the brain of the agent that guides the agent to next move. So actually, here is like a probability or a Q value if you're familiar with Q value. Or otherwise, it's just a probability of next move. So you choose your actions here according to this probability. And the target is just shown here. So the agent needs to review these things to find the brightest pixel. So now if you want, this is the game in action. So you can see this is during the text time. And then we have trained the agent for like 10,000 episodes. on different digits, and then during the text time, it always explore on the central part of the image, and then just after 2 or 3 steps, it finds the targets. This gives us a good hope that we can use the same technique to solve the meta-learning problem. So now, if we go back to the meta-learning problem, what we need to do actually is the same thing. The agent needs to navigate in the red row to find the algorithm with the highest performance. For this, it needs its brain. So it needs the green part I showed before. And this probability actually is computed according to a Q value. So the Q value is actually the accumulated reward that once I'm in a state ST and take the action AT, and then the accumulated reward until the end of the episode. So here, what we want to do is that in the input, so we need to use a function to compute this Q value. So in our case, this function is a neural network. So input is the partially reviewed row, and output is the Q value, or the next move probability. And then in this setting, we have a split between chain and text. During chaining time, the agents faced to a new task sampled from the chain set. And then it does a forward pass with, to guide the next move, and then a backward pass for optimization. But once the agent is fully chained, we freeze the brain of the agent, and then we just enter the text time. Then during the text time, the agent faced to a new task sampled from a separated text set. And then you still get the row here, but now you just do a forward pass. You do your move. So there is no adaptation during the text time. So here are the results, the same results as before, but this time I will compare with this new RL scheme. So, yeah, I forgot to say something about the meta features. So we can also only use meta features to help the learning. So if you have meta features, you just append it next to your algorithms. So here we are going to present the same result on one data set, during the text time. And we compare active method, which is collaborative filtering, with these 2 reinforcement learning agents. In green is with meta features, and in yellow is without meta features. And always we compare with the random agent. So the random agent still has a very good performance on an average, but a very huge variance. So we're happy to see that our RL agent actually, if you consider all the quantiles here, actually it was at least as well as the baseline. Then now if we average everything, average all the text sets, so here we have only 9 because we have 30 total. So if we do a 30% chain text split, we will meta chain on 23 datasets and test on 9 datasets. So here is the average performance over these 9 datasets. So we still see that our method, collaborative filtering and RL agents, still was at least as well as the baseline. And with this, with the error bar we show here, actually we can say, okay, I actually cannot conclude if using meta features help or not. Then now let's look at the OpenML. So here I only compare Oximeter with RL without meta features. So still, we are very good. We are very good compared at least as well as the baseline, the blue one. But still, if you look at the error bar here, I cannot conclude if active method is working better or reinforcement learning is working better. But the reinforcement learning looks like a little bit better than the active method. So the three takeaways from this series of experience is that first, we're happy that with our active method, so the collaborative filtering or reinforcement learning agents, we have matched the performance that a random search achieved on average. This is actually impressive because the random agent has a very good performance on average, but with a very huge variance. So sometimes if you are lucky, it can be good, but sometimes it can be very bad. Second is that our RL agent was at least as well as the very strong baseline collaborative filtering, and we were hoping that with some more effort, we can exceed it. And even we cannot exceed it, actually the RL agent is still interesting. Why? Because we don't need to do the matrix factorization during the test time. We don't need to redo it, so computationally it's more interesting. Okay, conclusion, I'm in time. Meta-learning is likely to become even more important if we want to take AutoML to the next level. Active meta-learning can be formulated as an MDP, or more particularly as a review game. NTP problems lend themselves to reinforcement learning solutions. And the first experiments show that RL delivers policies achieving results comparable to collaborative filtering while being computationally more efficient during the test time. And systematically, studies on larger data sets are just underway. So thank you.
Okay, I will start.
Okay.
So in your second approach, when you do active meta-learning and you represent your problem as you see your problem as a Markov decision process.
Yes.
You use the Q-learning. So I was considering the other kind of approach where you do hierarchical multi-arm bandit. So is it an approach you have also considered? Also, it is time-consuming.
Sorry,
Hierarchical multi-arm bandit, so Monte Carlo tree search.
Okay, actually, people have done that before, but it's not in my considering because we try to use the reinforcement learning here, but there's a possible solution.
Okay, and do you take into account so you want to go as fast as possible in order to get the best performance?
Yeah.
The number of trial as reduced as possible. And do you take into account this time?
Yes, good question. Actually, yes, because if you remember, we have a factor here, alpha here. So actually, this is learning a trade-off between how much time you spend for this and how much improvement you get. And actually, we have results here, but I have no time to show here, is that actually our agent is able to adapt this change. So actually, this alpha it depends on the user, because sometimes you prefer to have a good performance, sometimes you prefer to have an efficient method. So use another good point to use the reinforcement learning agent is we can adapt this easily. Yeah, I have some results if you are interested. Yeah.
Thanks. Other questions? Okay, so if not, we are going to leave questions for the break and the lunch. I think there is no spotlight Okay, so we thank you again,
Okay.
Lisheng.
Thank you.